Hello and welcome back to Calculus 3. We are continuing our chapter 13. Yes, with the section 2. We are working on double integrals currently. So we are going to take a look at general regions. General region meaning we have domain which is not a rectangle now. Anything can be in the domain. And yes, if we are able to I thought you left.
We didn't know you started.
No.
Still here.
All right, so 13.1
I didn't know how to do it either because I didn't know how to set it.
domain is a rectangle that goes from A to B, from C to D. And then we set up our integral. For 13.2, domain, meaning the region, would be something like this. You have a function f of x, and you have a function, let's say, g of x. And then whatever is the intersection of those two would be the region R. So what this calls for is to have functions in the integral. Now I will remind you that the integral of a to b of f of x dx that we used to have, right, was calculating area, which was also being calculated by the double integral a to b c to d of dA without a function. Now, the interesting part was, if you remember the problem that I did with the rectangle and looking for the area of that rectangle, that the inner integral, actually I can switch back to it, that's going to be quick. There it is. I did this problem in 3 different ways, 4 different ways if you count different. But I want you to observe 2 instances here. Calculus 1 setup and then eventual Calculus 3 step. They're identical. And I say eventual Calc 3 step. So you see that the numbers in here, right, 3 minus 1, were limits at one point. So now what we are going to get with the new integration technique here is that the functions, these f and g functions, are in the limits of the problem. So actually, I'm going to get rid of this so it's not confusing. Let me work off of this picture. So if I am to use Calc 1 to set up that, I would write there a and b where these intersections are. I would write that integral a to b of f of x minus g of x. So no. G of x minus f of x, right, top minus the bottom, times dx. All right, so that was the Calc 1. Now look what I can do in Calc 3. I can write the double integral, keep my a and b on the outside, and now put these guys, f of x and g of x, in the limits of the inner integral, and f divide dx. Gives the same thing. gives the same eventually. Think about it. If you are to integrate the inner integral, you will get integral a to b of y computed from f to g dx, and then when you plug in these two functions for y, you get integral a to b g of x minus f of x dx. So that's that part where I said it's the same, right? It seems that the general region, right, that we have, which is going to be bound by some functions, the general region can be also placed in limits. And one thing that, once I write the formula down, one thing that we are going to be very careful on, especially when we are setting up these problems, is we're going to have to look closely and carefully into the region, making sure whether our functions that are given are y equal f of x or x equal f of y. So we'll have to deal with that. Other than that, just good old regular integration, nothing special. So what do I have now? For these general regions, I will have double integral a to b f of x to g of x of some function, maybe age of... Actually, which letters they're using in a book? Are they using f and g in limits, or they're using g and h? I think they're using g and h in limits. I don't have the book with me. I think it's g of x and age of x in a book, and then they say f of x y over here, and then obviously you have dy dx. So I'm pretty sure this is the deal. And g is in the lower limit, right? Good. Equivalently, I can have c to d, and now this is going to be g of y, age of y, f of xy, and then dx dy. We can have that as well. And both of these will give us some kind of volume, because we have 3D. Now I would like to draw this so we can see what's happening. So I'm going to place two functions in here. They intersect at A and B, right, to these 2 points. And we are going to call the top function, right, age of x, and the bottom function g of x. Observe what's happening with the representative rectangle. Now, guys, if you're not drawing representative rectangle and you're not understanding this, you're going to have a very tough time setting these things up. So representative rectangle is just one of infinitely many rectangles that start at A and populate every single location all the way through B. So first representative rectangle is at A, infinitely thin, and then infinitely many rectangles follow all the way through B. They're all vertical representative rectangles. And this rectangle is what helps me set up the integral every time. I also need you to understand that this is just the domain, this is just the region. The object is here, right? The object is coming out of the screen, right? It's perpendicular to the screen. This is just the shadow of the region under the object. That's all it is. So this whole xy plane is the domain, is a region. So I can actually shade this and say R, right? R, region R. Now, how does this rectangle help me set everything up? Well, this is how this works in my head, and then if you find a better way, share it. I see that I must use a representative rectangle dx. If I try to draw dy, which would be horizontal, you see that the two edges of dy would be hitting the same function, and that's not allowed because you can't integrate, you get 0, right? You will go top limit, which would be h of x, minus the bottom limit, which would be also h of x, and that would subtract to 0. So we can't use, in this case, dy. We must use dx. If dx is the main one you are using, that goes at the end. And now dx starts at at a, and ends at b, hence the limits a and b. So the process of the train of thought is always you look at the shape and you decide whether dx or dy is the appropriate rectangle. Once you figure out that dx, sometimes both work. In this case, only dx works. So now that you have picked, yes?
Will dx ever not work?
Of course, in the next example. So you have the dx, which goes at the end, and then dx is trapped between a and b. Now, we also know from previous calculus courses that we have area between two curves, which is top minus bottom. Now look, top of the representative rectangle dx is hitting the h function, and that's the upper limit in a setup, and the bottom is hitting the g function, which is the inner integral there. So that's that part. So this is the way I use representative rectangle to help me set up the problem. So we'll see the y as well. Now also the last part over here is we are making sure, right, a and b are clearly on x-axis. So we have x, x, x on the outer integral. That all matches. Now let's see if the inner integral is y. So the inner integral is dy, so the inner integral here must be y. And it is, because y is equal to h of x and y is equal to g of x. So I hope you will stop for a second, right, and think about that, the outer integral is in terms of x, so your limits, your integration are both x, and you have dx. And then you move one inside, and this one is y variable. Well, you better have y1 and y2 in your limits. And you do have y1 and y2 in your limits because it is h of x and g of x. That's y equals h of x and y equals g of x. And now, to make you happy, right? You asked, is it ever going to be that delta x doesn't work? And the answer to that is yes. So if I draw the same two functions, but now I draw them sideways like this, if you try to draw delta x, you see that it's going to miserably fail, let's say here, because the top and the bottom are touching the same function. That's not allowed. Representative rectangle can never be trapped in between the same function, the function that, or line that curves on itself. So the appropriate rectangle for this one is going to be this horizontal.
Does that mean dy?
That means dy. Perfect. Which is this case. So I have my region R, right? I'm trying to do the pirate there every time. So I have my h of y and my g of y. So if you look at this carefully, you will see that the bottom, the lowest this representative rectangle can go is value c, and the highest this representative rectangle can go is value d. So c to d. And that's on the outer integral. And that's y, right? So you have the correspondence of y, y, y on the outer integral. Now if you look at the inside integral, it's going to be x, 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 right? You have the x1 equals to g of y, x2 equals to h of y, and then you have also x as a variable in the x part. Now this is tiring to erase. There we go. So that's the way we set up these integrals. And then a lot of this will depend on situation you have. So this is where the design, right, kicks in and you figure things out. But the most important part, at least at the beginning, is to realize that you shine the light on the object, like on that printer. You shine the light on that printer over there, and it's going to give you a rectangular base, and you know it's 13.1, right? But if you take the mouse, right, you take the mouse, and you shine the light on top of the mouse is going to draw up a shadow like that, right? And now you're looking at this and say, all right, so do I have some functions? Sure, you have some functions, right? You can cut this way, you have a function here, and then you have a negative of that function here. So you will call this one h of x and this one g of x, and then you will go and do the subtraction and so on. It doesn't matter what kind of object you have, right? Clearly, I mean, as long as you can model the functions. That could be clearly an issue if you can't do that. So, mechanics of solving these integrals is identical to the previous one. You deal with the inner integral first, and then you're dealing with the outer integral first. Let me write something in blood first. Changing order of integration is not trivial, meaning you can't just swap. Sometimes it cannot be done. So, at best, you will have to do some work to change the order of integration. In some cases, you won't be able to change order of integration at all. That should be obvious from these two pictures. There is no way, comma, in hell, comma, to set up dy integral here, and there is no way to set up dx integral here. So for these two cases, at least, neither of these can swap the order of integration, unless you do some additional magic. But it really, yeah, just don't, okay? But I'm going to go through a problem now where changing the order of integration works. For instance, say that my domain is a simple triangle. So I have region R given as, we can make up anything here, There we go. So this is 1, 2, 3, 4. 2, 3, 4, 5, 6, 7. 7.5. No, 8. 8. So now I have the region R. Well, in order for me to do dx integral, I need to have equation on the line on top, right? The equation of the line on the bottom with x-axis, which is just y equals 0. That's easy. But the one on the top, we actually have to figure out. So if I have dx representative rectangle, I would have to go and say, all right, so this line here has the slope of rise 4 units, sorry, drop 4 units, and then run 8. So slope is equal to negative 1/2. Y-intercept, you can just look at it. It is b equals to 4. So the equation of the line is y equals negative 1/2 x plus 4. That's the equation of the line. So now that I'm setting an integral for double integral of some function, I'm not specifying which function, because I'm only working on, for now I'm just learning how to set up integrals, and then the solving is the same. You solve the inner one and then the outer one and you walk away. All right, so I put in a dx, which means that this must be dy dx. Whatever is the rectangle you draw is the one that goes on the outside. So we put dx up there, therefore dx goes on the outside, dy goes the inside. Then we match the limits. Observe that x goes from 0 to 8. Right? X goes to 0 to 8. And then my inner limits are y1 equal to something and y2 equal to something. Now that is the subtraction top function minus bottom function, which means top function goes in the upper limit and the bottom function goes into the lower limit. So this is 0 and then negative 1/2 x plus 4. So now I have my x, which goes from 0 to 8, because the representative rectangle, the first representative rectangle is in the place of y-axis. And then all of the infinity of those infinitely thin representative rectangles, right? All of those infinitely many, all the way to 8. So that's why x limits are 0 to 8. Y limits are what's happening with the top and the bottom of the representative rectangle. The top of the representative rectangle is hitting the function, which is the one we figured out. So that's the upper limit. And the bottom is hitting x equals 0. I'm sorry, y equals 0, which is x-axis. Therefore, 0 goes in the denominator. Denominator. 0 goes in the lower limit. Much better. So now, if you just write this out, this is the integral that you will be dealing with. Now, I didn't give you f of xy. I didn't give you f of xy, so we can't compute this. I am focusing only on a setup at the moment. Now, in green, I am going to set up dy integral. So now I have the same stuff, right? Except now it's dx dy. So my outer integral is y, which means what are the limits on it? Anyone? 0 to 4. Very good. The first representative rectangle is at x-axis, which is y equal to 0. And then it goes all the way up to y equals to 4, and then that's it. We are done with those. Now, what's happening on the inner? Well, for dy, it's right minus left, right? Right minus left. So right goes in the upper limit, and left goes in the lower limit. Now we see that the left is 0, so that's not a problem, right? Yes, we have to solve this for x now, because these inner limits are x1 equals to 0 and x2 equals to, well, it's the line. And that line needs to be now solved. So I am going to move negative 1/2, so positive 1/2 right to the left is equal to 4 minus y, and then multiply by 2. So what I'm getting over here is x is equal to 8 plus 2y. So, to write it clean, 0, 0, 4, 8 plus 2y. That's what I said, please pay attention. People, it's clearly a minus. Like, no matter where you look, it's clearly a minus. dx dy. So I don't know if I can stress it enough, but y, right? Those are all on the outer integral. So y equals 0, y equals 4, and then dy. X, x1, x2. So the inner integral has limits x1 equals to something, x2 equals to something, and then dx. Great. Now, please don't write this, because it's going to be terrible. But if you try to simply swap, first off, understand that when you integrate the inner one, you will be plugging in the top function as a limit of integration, and you will get the integrand to be in terms of x. And that's good, because the next integral in the row is the dx, and you will hit the x function with the dx and integrate it out, and then use the numbers 0 and 8 to come up with a solution. I don't know, 3/2. Now, if you simply swap the order, which is what you are not allowed to do in this case, you see that you get garbage. Right? You get garbage because look what happens if you just swap. You get your so look, I don't even know where to start with how much of the garbage this is. You integrate the inner integral, right, in terms of dx, and that will integrate out because the inner limits are numbers, right? So for the inner integral, you are going to get like 6, let's say. And then you're going to hit that with the y integral, so you'll have 6y, and then you will plug this, and then, right, your answer will be in terms of x. And you were looking for a number to be a volume or area or something. So you can definitely see that you are never, ever, ever allowed to have a function on the outer integral. 100% of your integrals in Calculus 3 will have numbers on the outer integral so that you can get answer of 3/2 or a 6 or pi, right? So that's why this is, it's much harder to swap the order of integration, and every time we'll include this very important calculation that I did on the margin over here. If I have to swap order of integration, then your functions need to be able to allow for that, which means they have to have inverse. And this function here is the inverse of the other one, which is the reason why we are able to swap the order of integration. So how complicated are those problems? They can be very complicated. You get the integral, then you have to look at the limits and create your own picture, right? That triangle, that's not given. This is given. So you look at this, and you draw that. And you look at dx, and you put dx. And you say, no, I don't want dx, I want dy. You first see if it's possible to have dy, and if it is, then you have to do the inverse for functions and all of the other stuff, and then write the other integral. Changing order of integration could be a living nightmare for general regions. For rectangular regions from yesterday, joke. We just swapped them. That's it, right? Because what happened when this had a number as well? You swap them and this other has a number. So who cares, right? They both had a number. So that's the part on general regions being a bit tougher. So let's just take a look at, examples. But there's nothing else to talk about other than know your regions, know your basic functions, know how to compute the integral, right? And you're good to go. So here we go with some examples. Textbook has over 100 examples for you to practice. So let's go with the first practice example. Evaluating integral. I know how much you love trig, so let's start with trig. This is problem 21. It's just for you. Negative pi over 4 integral sine x to cosine x dy dx. Go. Compute the inner integral first, and then compute the outer integral.
This is supposed to come out to a number. Right? Yeah?
If you got 7, it's wrong. I can tell you that right away.
Oh, no,
Look at it. You should know all the numbers.
Do you know how to read?
Yeah, you know how to read a number, right?
Do you know how to read a number?
I don't know what I got.
I got unanswered.
which is
Square root of 2.
Yeah. Probably it.
which one?
Square root of 2.
Square root of 2.
I suck at that.
I have no clue. You have square root of 2?
I got 0.
You got 0.
Sine of negative pi over 4 is negative square root of 2 over 2. So when you subtract square root of 2 over 2 from negative square root of 2 over 2 from square root of 2 over 2, it's 2 square root of 2 over 2.
They have a double negative there. I don't know, I haven't done it, so.
Now you make me feel like I lost a negative.
No, you're right. It's which I almost said.
That actually makes it worse on my part, because then I think I lost 2 negatives.
Wow.
At least, you know what?
Well, wait, wouldn't that cancel out and then just have a correct answer?
As
Yeah,
long as
well-
you arrive at the right answer.
Yeah, because I think I have the right answer, but I don't
That's
think I
the
did it
that's
right.
the best when you make two mistakes that actually cancel each other out, and then you just get a right answer at the end.
What did you get? 4?
Yeah, that becomes.
Anyway, let's see.
I don't know.
I got root 2.
So the inner integral,
Someone else got root 2.
the inner integral is just going to be y, because we are integrating 1. I can put 1 there if I want to.
Oh, that's why I missed it all.
So if when I integrate 1, I get y
Yeah.
from sine x to cosine x, and I still have to deal with dx eventually. So integral negative pi over 4 to pi over 4. And then I have cosine x minus sine x. When I plug these in, I have to put parentheses because dx needs to multiply both of them. So those parentheses there are necessary. Otherwise, minus 1 on notation.
What's necessary?
Parentheses.
Okay.
So now, cosine of pi over, no, we have to integrate.
Yeah.
Yeah, I almost pulled. Yeah, I almost pulled carry.
Why?
I was about to plug in pi over 4 without integrating.
Oh.
Yes. The integral of cosine is sine x. Integral of sine is negative cosine, but negative and negative makes it a positive cosine there. And then negative pi over 4, pi over 4. That will be $1 right there.
Oh, I'm sorry.
So now, square root of 2 divided by 2 plus another square root of 2 divided by 2. Now, minus, and minus gives me square root of 2 over 2. And a cosine kills the minus, so it's minus root 2 over 2. These guys would die, and we have root 2.
I found my mistakes.
I can't believe you dropped 2 negatives. Wait.
I started doing it in my head at the way end. So I'm like, this is
Okay.
not
I
a lot of stuff.
can't do that because I know all this stuff.
Apparently I can't either, so.
I got it.
Next problem is going to be exponentially spicier.
Oh, we love one. All right.
I don't know, I like a wild.
Compute
Oh.
the integral of a region R, where R is bounded by R is bounded by x equals 0, y equal x squared, and y equals 8 minus x squared.
Thanks, I hate it.
Don't know how to do anything.
Well, I'm going to guide you through this to see how much you can accomplish. First off,
Don't have high expectations.
I am having high expectations.
All right. Love
Job number 1 is to take those 3 equations and graph them on the same coordinate plane to come up with the region R.
R.
Yes.
It's not as funny as you think it is.
What? No, it's not. I know. That's why I do it. That's
After the lecture, can I bother you about the physics problem? Because I think I never read one of them, so I will.
Was the physics problem supposed to be?
No.
Oh, you know,
I thought I did it wrong.
Messed up,
I was supposed to get it.
but I know I messed up.
Together, it's two parabolas, and then a line going
I
right
think.
down the middle of the two parabolas.
I had like
I guess
three
I think
lines,
since it's an area,
and
Okay.
the first
I was looking at other problems.
Sounds
Like
correct.
I
I
knew
don't
I
even
got
have
the
to
other
put it.
one wrong.
I feel like
so I just took that
equal of those are
Also, if we solve, like not for this, if we solve one of the other ones with the wrong method and get the right answer, do we get credit?
Yeah, but what do you mean wrong method?
What do you mean? I mean, if you got the right answer, it's a wrong method?
It was like from how one, because I kept on getting 0 for something. I figured out why at like the way end, why I kept getting 0. But I just did like
Was this the...
box.
Oh,
Which side?
I'm not entirely
Either
sure I
side
got that
matter
right.
because there's a
I got like 4. That's that.
kinda.
I'm not sure I got it the right way. What is it? That, I had a
In the first
I
quadrant.
like, literally got 12 in Calc 1, and I looked at like...
I was coming at you.
Oh, the first quadrant?
Q1, first quadrant.
Well,
Yes.
that's helpful, because I like...
Yes, it is.
I tried to use the signs, and then it like kind of worked, and then I kind of messed it up, but I figured out where I messed it up, I think.
Yeah. I did something really stupid with that one. I forgot that 8 was a variable. So literally all I got, I tried it
I
like 4
just
different ways.
simplified it
and I got-
because it was like, it's a square base, so instead of having x and x, you get x squared.
Yeah.
And that simplified it. I used to have a list.
You won't be able to
follow. I drew arrows at the end to
Well,
try
now
and help out,
really
but
unfortunate and
I
funny.
sort of just, it was like, look up at the book, and I'm just like, just come back over here. I don't know. I try my best. It's, you know,
I think you.
it's been a long week for me.
What do you mean? Well, same length for everyone.
Time is relative.
Oh yes, that's true.
I don't want to do things like is this a piecewise function? No, well, I can see it. There's
Where
got 3
is the
different lines.
intersection? That's fine.
Three lines, Jake. One of them is the y-axis.
Yes, I count that as
Our
one.
x equals 2. We're just gonna go with it.
Yeah, but like,
Please don't do it yet. I'm not done.
Yeah, the world revolves around you,
yeah.
and we are all going to wait. Sure. Let's do this together.
Wait, I think I'm gonna get. See? Other people.
Still irrelevant. Welcome to my class. Exactly. So say this is 8. It would be parabola that drops down, and then x squared is a parabola that opens up, and then we have x equal to 0. So I'm going to shade the region. R. Since it's annoying, I'll just make sure that it's every exactly. So now, if you look at this, you have to make the decision. The setup of the problem is dA, and yesterday I wrote that the dA is either dx dy or dy dx, and the one that it's at the end is going to be the representative rectangle you are using. So you have a choice of dx or dy. Now, hopefully, you see that dy is bad, because if you draw dy, and that's first thing that we're going to try over here. I'm just going.
I mean, isn't it just that since you have to have numbers on the outside?
Well, let's just first think of the geometry, guys. If I have to do this line all the way out, so it's easy to erase. Otherwise, I have to shade again. So representative rectangle dy, observe what's happening with the ends of it, right? The left end is always going to be sliding on the y-axis, which is x equals 0. So the lower limit will always be 0. But look at the other side. The other side is going to follow one function up to the point and then switch and follow the other function. Now, I'm not saying it's impossible to do it that way. It just spells you have to have two integrals for that. But why? We can just put dx, and dx will always be between the x squared and 8 minus x squared. So dx is a much better choice. Now, here, this is a situation where both can be done, but one is more convenient than the other. So you have, both are the same complexity, like the triangle problem. You have one not possible at all, which are the two pictures that I have earlier. And over here you have where one is more convenient than the other. So I'm going to use dx because dx, when I draw dx here in the region, the bottom always slides on x squared function, and the top always on 8 minus x squared. So when I'm setting my integral up, I have the x plus y, and then I'm using dy dx, and the inner integrals are 8 minus x squared on top, because the top is hitting the 8 minus x squared function, and the bottom is hitting the x squared. We know that the left limit for dx is 0, because that's the y-axis, also given to us explicitly here. But we don't know where this point is. What should I do? Find the intersection of the two parabolas. Very good. So, in blue, over here, x squared is equal to 8 minus x squared. 2x squared is equal to 8. X squared is equal to 4. X equals plus minus 2. Now we only need the positive 2, because that's on the positive side. Bueno? All right. So now we compute this. I am integrating in respect to y. So I have 0 to 2. We have xy plus y squared over 2, computed between x squared and 8 minus x squared. And I still have dx. So now this is going, yeah, these problems tend to be just, it's good for killing time and developing carpal tunnels. One of those things, right? So we have x times 8 minus x squared plus 8 minus x squared over 2 minus x to the 4th over 2 dx. You have to plug upper limits and the lower limits, so just figure it out. Exactly. So 0 to 2, open parenthesis, I have 8x minus 2x cubed plus 1/2 times, and now I have 64 minus 16x squared plus x to the 4th minus x to the 4th, and these will die. Everything dx. So I have integral 0 to 2 of 8x minus 2x cubed plus half of 64 is 32 minus 8x, good effort, x squared. There we go. And then dx And finally, we can write the entire problem. We have negative 2x cubed minus 8x squared plus 8x plus 32 dx. Yay! This is going to be negative 2 times x to the 4 over 4 minus 8x cubed over 3 plus 8x squared over 2 plus 32x from 0 to 2. Cancel what you can. That gives us negative 1/2 x to the 4th minus 8/3 x cubed plus 4x squared plus 32x computed from 0 to 2. And finally, we plug in 2 only, because 0, it's a polynomial, so 0 is going to kill everything. 4, that's a 16 divided by 2, it's negative 8. So it's 864 over 3. Plus, that's 4, plus 16. And plus 64. 16 and 64 is 80 minus 8 is 72. Minus 64 over 3. 216 minus 64 over 3. And that's 20 minus it is 14, 15, 2. That's what I said. Please pay attention. 1 plus 5 is 6 plus 2 is 8. It's not divided by 3. Good. 152 by 3. What is that? That's the volume of this object. My old charger for like the cell phone battery bank thingy was of this shape, so it was easy to show. What you have is, well, actually, maybe I can use this one, but it's not the same. So you have two parabolas that are intersecting, and it sets flat on xy plane. On top, it's cut at the angle with the plane x plus y. So that would be the object. And this number here is the volume of that object. That's what we computed. The last thing, I still have to say this. I know, yeah, you're packing and want to go, but I have to say this. This goes mainly for the advanced students here. Do not play with fire. And that fire is called symmetry. If you look at this picture here, and you say, oh, left half is the same as the right half, let me double it and get the whole value at the end just to be 304 over 3. Hell no. The top is cut at the angle. And if you cut something at the angle, it's going to have more mass, more material on one side than on the other. You can't double it. You see that? Only objects that are perfectly symmetric from whatever angle you look at them and cut flat on the top, yeah. But this one is cut the plane at the angle. And as soon as you have that, right, it would be clear that if you try to calculate the volume, right, well, this side has more stuff than this side over here. So it's not symmetric. If I draw a perfect symmetry line here on the object, clearly this side has more stuff than that side, right? So you have to be very careful with the symmetry. You are only looking at the domain. Now, I can bring that into 2D environment from your previous and ask you, when you are on a symmetric domain, from let's say -2 to +2, and you draw a slanted line, is the area in the left side the same as the area on the right side? you would immediately say, hell no, because clearly the one on the right is bigger. The same is happening now. You have a symmetric domain right to the left and the right in that picture, but the top is slanted, so you can't double it. You actually have to compute the other side separately. Now the problem asks only for the first quadrant, right? So it only asks for the right side. But if you have to compute the whole thing, if it didn't say quadrant 1, then you would have to compute both. And this was a fair warning to you guys not to double it, right? You actually have to do all this extra work. Yes?
Now, for this example, if you ask this calculate the other side, how do you got the answer?
Yes. You have to. It's not symmetric. You have to. So to battle, right? To battle the situation over here, if I asked if this Q1 wasn't there, the entire integral looks the same. This 0 is -2. That's it. But you are not going to get double what you have here because the top is slanted, unless the top is symmetric. And if the top is symmetric, then sure, right? So you have to be very careful about those things.
Basically, it has to be symmetric, but horizontally and vertically, right?
Or just symmetric on the right axis. I mean, I can slant, right? If you slant in a right way, sure, right? This desk is symmetric, and if I'm calculating the volume from left to right, if I cut it in half, I can calculate half and double it, right? Now, if I slant the top, right, this way, and I'm calculating from here to here, well, it's still symmetric, so because the cut is this way, so I can do it. But the other way cut, it will not work. It will not be symmetric. So if you have issues visualizing these things, if you're not sure which way x plus y slants as a plane, right, you can't really make these symmetry decisions. So that's why I'm saying don't play with fire, which is called symmetry. Just calculate everything long way, and you will get the problem right. If you know the symmetry, obviously, then you can play with that. And see you all in, 4 days, right? Monday? If you get nostalgic, my picture is on the Med Department website.